and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBV Electronic.
Welcome to the Passion for Technology podcast. Energy is the big issue of our time, and when it comes to energy, most people tend to think big. Wind turbines, photovoltaics, and the like. But energy also plays a huge role at a small scale in chips and electronic circuits. Analog integrated circuits, ICs, are becoming increasingly important. I'm joined by two guests to find out why. Chris.boyce is Senior Director of MOS Discretes at Nexperia. Hi, Chris.
Hi.
And Dr. Saeed Safari, Principal Field Applications Engineer at Broadcom. Hi, Saeed.
Hi, Mustafa. Thank you for having me.
Sure. Thank you both for being here. Chris, can you clarify why there's so much focus on energy? I mean, the components, small integrated circuits, they don't really consume that much power.
Yes, when you look at each individual component, indeed, they don't consume much power. But it's really just a question of scale. If you consider the system on chip that goes into a Xbox games console, that device is something that contains something like 15 billion MOSFETs. And each individual MOSFET obviously consumes this tiny amount of power. But when you put 15 billion of them together, then that single device can consume somewhere between 250, 300 watts. That's 3 times a 100-watt filament bulb, and you can feel the heat that comes off of that. And then you scale that up by 20 million gaming consoles a year, and then you scale that up by other applications like PCs, 1.5 billion mobile phones a year, all the cloud computing that's providing the infrastructure that's allowing everybody to listen to this podcast. It's a huge scaling exercise. And so each individual component may not seem so important. By the time you multiply it up, it becomes a very significant burden on the world's energy consumption.
Saeed, any more examples that cross your mind?
Definitely, yes. One of the example is AC to DC inverter. It is not uncommon to see an inverter with many isolation content. An inverter would need isolated gate driver to operate the power switch, isolated current and voltage sensor for the measuring, digital optocouplers for data communication. That is a lot of isolation content for one equipment. And it is also an easy way to lose power to dissipation if the selection of this isolator is not done thoughtfully. There are also other considerations regarding the selection of isolator in this equipment. For example, optocouplers generally consume power only when the LED is transmitting. This makes them a very power efficient choice for use case such as those with a low duty cycle transmission or application where there are significant period of the standby or inactivity. So as you can see, that's how a small, simple isolation IC can affect a large application that it is a part of that.
Chris, what methods enable semiconductor manufacturers to reduce the energy consumption of chips?
So if you'll allow me, I'll kind of focus on my area of expertise, if you like, which is the power components, the power MOSFETs that we produce at Nexperia. Typically, they're used in a couple of scenarios. If you consider the system on chip that I was talking about previously as a sort of brain of the system, the MOSFETs are used either to provide a power supply to the brain to allow it to function, or they're essentially the muscles in this system and taking a direction from the brain and then having to do something physical that requires a certain amount of power. Might be turning a motor, applying a brake, whatever it might be. In both of those scenarios, we're looking for MOSFETs that, as you go from one generation to the next, try to be more efficient, try to waste less energy in those power supplies and in those transactions where we're trying to convert that signal into a power output. And we do that in a number of ways. The first of which, the kind of headline figure for a MOSFET, is the on resistance. The power consumption when a MOSFET is on is basically a function of the current and the resistance, I squared R. So if you can lower the on resistance, then the amount of power that's dissipated goes down proportionally. Depends on the voltage range of the device, but we now have MOSFETs that are in way less than 1 milliohm when these devices are turned on. And that really helps with the conduction losses associated with any particular system. The other power loss mechanism is when you're turning the MOSFET on and off. When it's off, it's essentially dissipating almost nothing. But during the transition from off to on and on to off, as it goes through that transition, there is energy lost as heat and other functions there, which is related to the dynamic performance, the dynamic parameters of the MOSFETs, things like input capacitance, gate charge, etc., etc. We try to minimize those parameters to allow the switching performance to be as efficient as possible, to allow the device to switch from one state to the other as quickly as possible and with as little energy usage as possible. Putting those two things together, you end up with the on-state losses, the conduction losses, combined with the switching losses gives you the overall efficiency of the system. As we go from one generation of technology to the next, it's always those types of functions that we're looking to optimize and to squeeze every ounce of performance out of.
Saeed, focusing on the issue of power management, what pressures does that put on power components?
I'm looking at this question from two perspectives. Often we are concerned about the volatility of the energy consumption than the actual magnitude. I mean that if it is high, and we know it is, we would have designed for it. But to deal with the unpredictability and wide swing, this calls for the real-time information. This is also why we have been expanding our lineup of current and voltage sensors. Traditionally, customers have only a need to have this sensor at the output of the inverter to make sure the output values are exactly what they want to be. But in recent times, more and more customers have been making a request to have these sensors to monitor their incoming power as well. So analog IC do play important part in the power management. My second perspective is how about optocoupler? Are they getting more power hungry with a greater advancement and more features? Fortunately, this is not the case. In our smart gate drivers, for example, these additional features such as, for example, overcurrent feedback, undervoltage feedback, they consume negligible power. In fact, one of our key selling points for our newer devices has always been to be low power.
Chris, can you give us a practical example of how the interaction of power and digital ICs can reduce energy consumption?
Perhaps a very relevant example given Saeed's organization, Broadcom, an example there where Broadcom and Nexperia have worked closely together with our new GaN-FET devices. These are transistors made of an alternative to silicon that offers higher switching performance. And we've worked with Broadcom to develop a reference design that incorporates the gate driver from Broadcom and the GaN-FETs from Nexperia. And it really provides a reference point for the next generation of power efficiency.
Another major application of analog ICs is conversion of currents, especially in power electronics. Saeed, what major trends in terms of energy efficiency do you observe?
In terms of the conversion of the current, that also we name power conversion generally, we mentioned that the trend of the wide GaN device, and they are enabling higher voltage and power, higher operating temperature, faster switching, and better efficiency. For example, Nexperia is one of the main provider of the GaN device right now. Broadcom, as a gate driver manufacturer, is enabling this trend by building newer devices that will work well and is compatible with the various silicon carbide and GaN power semiconductor switch that you can find in the market these days.
Chris, what advances in technology are happening that help with saving energy?
So I think the really exciting developments here are in some of the new materials that are coming through. Things like silicon carbide and gallium nitride that we've just touched on. These devices offer a new level of performance compared to traditional silicon devices. They are different. We're at the real front end of their use in this industry. Silicon devices will be around for a very long time yet. But we do see in some of these more demanding applications that these new 3-5 materials, as they're known, silicon carbide and GaN, they're finding their place. And increasingly, the range of applications that they will be able to address in a cost-effective manner will only increase from this point forward as they become more and more used in volume. Take a couple of examples. If we just look at the electrification of transportation, electric vehicles, the need to reduce range anxiety in consumers and the new applications we find in these electric vehicles, I don't doubt that we will see an explosion of power GaN devices and silicon carbide devices already active in things like onboard charging applications, DC-DC converters going from a 400 or an 800 volt battery down to a 48 or a 12 volt bus, and ultimately in traction inverters themselves, the things that actually provide the drive to the wheels. There are some non-automotive applications, things like titanium power supplies, which offer the really highest levels of efficiency. Some of the topologies that are being proposed to deliver these levels of performance are only realizable when you use some of these new materials. I'm very excited about the opportunities that Power GaN and Power SiC bring into the marketplace. They present their own design challenges. You can't just unplug a silicon device and plug in a gallium nitride device and expect everything to immediately see the benefits. You have to work quite hard. So there's some engineering effort around making best use of this. But best companies and the best engineers will find a way to exploit this new technology to create better products.
Saeed, what's your take? I mean, can the energy consumption of ICs be reduced even more? Where are we heading?
If you look in the trend of the reduction of the energy consumption of the IC in the last 40 years, 50 years, you will see that that is happening. The energy consumption of the IC has been reduced. And something that I will see in the future that, again, this is going lower, and that is done with a different way. One of the things is about, for example, newer material that we will have in the future, and also for example, architecture of the system. So I think we couldn't say right now is the end of the reduction of the energy consumption for the IC. I think we will see more in the future about reduction of the energy consumption of the IC.
Thank you. Thank you both for the insights that you shared with us today. Now, before we close our show, I'd love to know when and how each of you developed your individual passion for technology. Chris, how about we start with you? When and how did you develop your passion for technology?
A fascinating question. I guess mine goes back to my childhood. My father was a carpenter. He left school at 14. He did a 7-year apprenticeship. And by the time I used to go to work with him, he could build a staircase from scratch. So I always had that interest in the practical side of engineering, if you like. And as I went through school and I found I was okay at maths and physics and those kind of STEM subjects, I really considered my education as a kind of modern day apprenticeship toward the technology of the time, which at the time was all about electronics. And I remember very distinctly seeing a careers advertisement where some guys at university had built a dartboard that could automatically score. And I loved the idea of figuring out physically, how do you register where the dart has landed? And then how do you build the electronics to do the subtraction from 501 down to 0? And it was at that time I thought, yeah, I'd really like to have a go at that. So yeah, in my childhood, I guess, growing up on building sites is where it started.
That's a beautiful story, from carpentry to auto-scoring dartboards. So Saeed, what about you? Where does your individual passion for technology come from?
For me also, I think that's happening when I was a child, when I was especially in the secondary school, that I started to learn about the electrical engineering and electricity, for example. Then I found it that, for example, we have a different sort of the voltage source, AC voltage source, DC voltage source. Then I see that there is a different shape. When they sketch it, there is a line, then there is an AC with a different frequency. Then I understand that later, okay, they can be converted from the DC to AC. For me, maybe at that time it was very something interesting that something very straight line as a DC, now we can convert it to something with a very different frequency, and then we can use it in different application by doing this one. And same thing, it was energy for us, is what electrical energy, but by changing the way that they have, and then applying to the different application, then we reach to the something that we needed, for example, charging the battery, and then the electrical can move it, or for example, as a light, for example, you can see it, or in the different appliances that you have in the house, for example, there is a motor, then the motor inside that moving. Actually, I was so much interested to know that how we can have this conversion between different sort of the electrical energy as an AC source and DC source that we have.
Super interesting. I mean, once you plot these waves, things do become interesting, and all of a sudden you realize how you can approach them with math, and then things fall into place. Very interesting origin stories that you both had to share. So thank you, Chris. Thank you, Saeed, for the insights that you shared with us today. Dear listeners, if you'd like to get in touch with either Chris or Saeed, feel free to reach out to them on either LinkedIn or via email. We'll be sharing all the details with you in the show notes. Please also feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Thank you, and thank you both for joining us today.
Thank you very much.
Thank you very much.